Okay, good afternoon to you all. So hope you can hear me, right?
Yes, madam.
Okay, okay. So in the last lecture, so we were discussing the first chapter under the Introduction to Probability and Statistics 1. So we are just discussing the basic concepts of probability. And in the last lecture, we discussed about counting rules, fundamental counting rule, permutations and the combinations, as well as how to obtain probability values using a contingency table, right? And then we discussed some properties of conditional probability. We discussed what is a conditional probability, and under the properties of conditional probability, we discussed about multiplication law, and also there are two other theorems or rules called total probability theorem and the rule of total probability and the Bayes theorem, right? So all the things, the conditional probability involves in multiplication law, total probability rule, as well as the Bayes theorem, right? So wait, I'll share the screen. Yes. So we discussed what is a conditional probability, and then properties. Under the properties, the multiplication law we discussed earlier, and next two properties were total rule of total probability and Bayes theorem. So both the Bayes theorem as well as the law of total probability involves when when a partition of the sample space exists. That means when the sample space has been partitioned into some groups, right? So when there is a partition in the sample space, and when there is any event given, and also the conditional probability is also given, that means given the partition, another event occurring, the probability of another event occurring, that is the conditional probability. So in that case, to find the probability of the unconditional probability of the second event can be calculated using law of total probability. So the basic things you have to remember is when there is a partitions in rule of total probability as well as in Bayes theorem, the sample space has been partitioned into several groups, and there is another event has been occurred, and conditional probabilities are given. That means when the sample space has partitions, it is given, and another event has been occurred. So the conditional probability is given. So you have to find the unconditional probability of the occurring of the second event, right? So I discussed it using a Venn diagram also. So this is the sample space. So it has been partitioned into several groups, right? And another event has also been occurred, right? Let's say this is A1, this is A2, A3, A4, A5, likewise. The sample space has been partitioned, and another event has been occurred, right? So we have the conditional probability of occurring B, the partition always has been happened. Those probabilities are given, right? So we have to find the unconditional probability of event B, that means P, PB. I think there is some problem with my pen. Sorry for that. So we have to find the unconditional probability of the event B. So that is the rule of total probability, right? So the rule of probability, the equation is given here. So we are finding the unconditional probability of the event B. Okay. So we discussed an example. The members of consult. Yes, we discussed this. No need to discuss it again, right? So, yes. So in that example, the sample space has been partitioned. It is said there are 3 rental agencies, right? The cars, so the sample space has been partitioned into 3 groups as agency 1, agency 2, and agency 3, right? So let's say this is A1, A2, and A3, right? And the second event is the car need an engine tune-up, right? Car need and tune-up. So this is event B. Car needs a tune-up, right? So the conditional probabilities are given. P, B given A1, PB given A2, and PB given A3. Those information are available, right? It says 60% of agency 1, if 9% of the cars come from agency 1 need a tune-up, that is PB given A1. 20% cars come from agency 2 need a tune-up, that is PB given A2. Likewise, from agency 3, PB given A3. Those probabilities are given. The question was, what is the probability that rental car delivered to the firm will need a tune-up? So we need to find what is PB. What is PB? Right? So that is the unconditional probability of the event B when the sample space has partition, right? So now, what happened if a rental car delivered to the constituting firm needs a tune-up, what is the probability that it came from rental agency 2? Right? In earlier case, they have provided the information P P B given AI, right? Now they are asking, the car has already found that it needs a tune-up. That is the given one. That is P B is given. What is the probability that is came from rental agency 2? Right? So this is the problem they are asking for. Okay, so this is called reverse conditional probability. So Bayes' rule is used to calculate what are informally referred to as reverse conditional probabilities, which are the conditional probabilities of an event in a partition of the sample space given any other event. So we are using the Bayes' theorem here, right? So Bayes' theorem, it says, let A1, A2 up to AN be in mutually exclusive and exhaustive events with PAI does not equal to 0 for all, so that A1 union A2 union up to AN equals S. That means the same information given you have given earlier, the sample space, when the sample space is S and it has been partitioned into N number of mutually exclusive and exhaustive events. So the union should be equals to the sample space, right? The sample space, i.e., that means a partition, that is a partition of the sample space S, and PAI does not equal to 0, and B be any arbitrary event of S such that PB greater than 0. So again, the same scenario, the sample space has been partitioned into N events, mutually exclusive and exhaustive, and there is any arbitrary event called B. So then PAI given B is equals to PAI into the conditional probability of PB given AI divided by, this is PB, right? This is PB, the total probability of occurring event B. This one is PB. I think you can remember here. See, this is the total probability. Okay. So that is the Bayes' theorem. So this is an extension of the results P, B given A, the conditional probability, right? So in earlier case, in the conditional probability, we discussed where the sample space has not been partitioned, but here the sample space has been partitioned, right? So this is the interpretation. I think now you have the idea, but this is clear when it explained by the tree diagram. So in this tree diagram, yes. So this is the partition, the first event. The sample space has been partitioned into N mutually exclusive and exhaustive events. And then when A1 happens, A1 has been already happened. What is the probability of happening B. That is the conditional probability, right? So it is PA1 intersection PB, sorry, PA1 intersection B. It can be written as A1 into PB given A1 using the conditional probability. So it is the probability associated with the first branch. So this is the probability associated with the second branch. Likewise, this is the probability associated with the nth branch. Sorry, ith branch, and the last one is the nth branch. So we can obtain the total probability by adding up all the probabilities, right? We can find the total probability of occurring A, right? There are n number of ways to occur B. So adding up all the values, we can obtain the total probability of happening the unconditional event B, right? So this is the total probability. And the probability that the event B was reached via ith branch of the tree diagram, given that it was reached via one of its n branches, is the ratio of the probability associated with the ith branch to the sum of the probability associated with all n branches of the tree. So this is the Bayes theorem actually. So the Bayes theorem gives you the probability of occurring AI given B. So it can be obtained using probability for the path through AI and B divided by sum of all probability for paths to B. So this is the explanation of Bayes theorem using the tree diagram. Okay. So I think it's clear now. So the proof has been given. So the sample space has been partitioned here, and another arbitrary event is given as capital B. So by definition of the conditional probability, we can write, we need to find AI given B. Using the conditional probability, we can write this equation, and using the multiplication law, we can write PAI intersection B like this. And we know that since B is a subset of union of AI. So union of AI is the sample space, right? So B is inside the sample space. So it should be a subset of union of AIs, right? So we can write it as B is a subset of union of AI. And then since it is a subset, we can write it as B intersection union of AI, right? So it can be written as union of B intersection AI. And then we can write the probability of B. We apply the concept of probability to the upper equation, this one. So we can write it, write the probability value as probability of unions of B intersection AIs. So using the additive law, right? Since there is a union, we can use the additive law. Using the additive law, we can write this as a summation, right? Summation of probability B intersection AI. So B intersection AI can be written using the multiplicative law as PAI into PB given AI. So now we can substitute these 3 and 2 to 1 and then obtain this Bayes theorem equation. Okay, right, I think it's clear. Okay, now you know what is the Bayes theorem. And before going to this example, I think we had an example earlier, the rental car delivered question. So try this one. Try this question. Now we have the total probability of occurring B, the unconditional of probability of the event B. So try to find this. Right? So this should be the answer, right? 0.5. So when it is given that the rental car delivered to the constituting firm needs a tune-up, the probability that it came from agency 2 is equals to 0.5. Okay. Okay, try this example too. I'll give you yes, nearly 10 minutes, 7 minutes. Try to obtain an answer for this example too. Okay, someone has asked me a question. PA2 given B equals PA2 intersection B upon BB. Madam, cannot we use this to solve this problem? So again, PA2 intersection B means PA2 into PB given A2. And PB is the total probability. Right? So it's same. Again, the Bayes theorem. Okay. Is it clear now? Finished? Send me answers. Those are finished. I think this is little bit confusing, but try to understand what are the what is the partitions of the sample space. So actually here the partitions, there are two partitions. No, it's not. Yeah, Imasha. Yes, you're correct. Okay, I'll explain it, right? Okay, consider a test that can diagnose kidney cancer. The test correctly detects when a patient has cancer 90% of the time. Also, if a person does not have cancer, the test correctly indicates so 99.9% of the time. Finally, suppose it is known that 1 in every 10,000 individuals has kidney cancer. Find the probability that a patient has kidney cancer given that the test indicates she does. So initially, you need to identify what is the partitions of the sample space, right? So it is given that it is known that 1 in every 10,000 individuals has kidney cancer. So is it an conditional probability? Is it a conditional probability? No, it's unconditional probability, right? So that should be the partition. Okay. So initially, the sample space has been partitioned into two. Let's say A1, A2. Right. A1, A2, right? So that means kidney cancer. Let's take that as A, the event. Okay. Then if we take having kidney cancer as PA1, right? It is given that 1 in every 10,000 individuals has kidney cancer. So it should be 1 upon 10,000. That is equals to 0.0001. Okay. Then this is patient having cancer. patient having a kidney cancer, right? So then we can obtain individual does not has a cancer, it is PA2, and it is the complement of PA1. Sorry. It is complement of PA1. That is 1 minus 0.0001. It should be 0.9999. Okay. Then if we consider test positive for cancer as B, the event test positive for cancer is B. So this is B, right? The test correctly detects when a patient has cancer 90% of the time, right? That means P, the given information is patient has a cancer and the probability of detecting it using the test is 90%. So it is PB given A1, right? It is 90% means 0.9. Okay. And another information has been provided. If a person does not have cancer, means the given information is again not A1 this time, A2. If a person does not have a cancer, the test correctly indicates so. That means if the individual does not have a cancer, test indicates that the patient does not have a cancer. That is the complement of B. Right? We took test positive for cancer B, but it's given here if a person does not have a cancer, the test correctly indicates so. කියන්නේ cancer නෑ කියලා test එකෙන් results එනවා කියන්නේ negative result එකක් එන්නේ. So that conditional probability is equals to 99.9, that is 0.999. Okay. Then what is the problem? The problem asked, find the probability that a patient has kidney cancer. Patient has kidney cancer, given that the test indicates she does. Right? So the given information is the test indicates she having the cancer. So test indicates positive, it is B. B given. Find the probability that a patient has kidney cancer, that is A1. So this is the thing we have to find. Okay. So according to the Bayes theorem, we can write it as probability of A1 into probability of B given A1 divided by probability of A1 into probability of B given A1 plus PA2 into probability of B given A2. So now we have PA1, PB given A1, PA2 and PB given A2. We need to find PB given A2. So here it's given the PB, the complement of P given A2. So using this, we can find P B given A2, that is 1 minus P B bar given A2, the complement, that is equals to 0.001. Right? Now substituting those values, we can find the question, the problem, solution to the problem. 0.0001 into 0.9 divided by 0.0001 into 0.9 plus 0.9999 into 0.001. So by solving this one, we can obtain an approximate value as 0.083. So what you can say about this test? So this is the probability of patient has kidney cancer given that test indicates she does. ඇත්තටම එයාගේ ටෙස්ට් එකෙන් පොසිටිව් කියලා එන්නේ කිඩ්නි කැන්සර් එකක් තියෙනවා කියලා එන්නේ. එතකොට එහෙම පොසිටිව් එන රිසල්ට්ස් වලින් එයාට කිඩ්නි කැන්සර් එක තියෙන්න පුළුවන් probability එක 0.083. So it's very low value. So the test is not much reliable in this case. Right? The test is not a good one to identify kidney cancers. So is it clear now? Any questions? Any questions up to now? Okay, so that is the end of the chapter 1. So I just recall the things you have learned in your A levels, A-level mathematics, the basic concepts, types of probability, probability rules, conditional probability, what is a mutually exclusive event, what is an independent event, and counting rules, fundamental counting rules, permutations, combinations, and the properties regarding the conditional probability, multiplication law, rule of total probability, and Bayes' theorem. So the next chapter we have to start is random variables. So I guess from next chapter onwards, you have to learn new things. So be in the lecture, right? So I think we should start the next chapter in next week. So I thought to give you a question, right? You have to solve the question using the Bayes' theorem. So I'll give you the question now. So you have 1 hour. So within that 1 hour time, so it's not actually take 1 hour, it just take 15 to 20 minutes, right? So write answers for the question, for the given question. I'll give you it now. Write answers and then you can upload your answer to the LMS. I have provided a link in your LMS. And you can either scan it or can scan and convert into PDF and then send, or either you can just take photos of your handwritten answers and then attach them into a Word document and then upload the Word document, right? No need to convert the Word document to the PDF as we do in tutorials. You can just send the Word file as well. So I'll give you the question. You have the time until 5:30 p.m. So in that point where the lecture ends. So try to, not actually try, do that question and send it into the LMS, right? Is it clear?
Yes, ma'am.
Okay. I think it's clear, the things you have to do, right? So I'll share the question now. Okay, can you all see this?
Yes, ma'am.
Okay.
Yes, madam.
Okay. Okay, try this problem, do it and submit into the given link in the LMS, okay? The time duration, you have 5:30 until 5:30 to submit. Okay, you can write any paper. You can use any paper here. I just need your answers. So wait. Attention, please. Please take a screenshot of this problem. Since I want to wind up the session, a Zoom session now. And then you can try the problem, right? Please take a screenshot or a photo or anything. Okay. So, okay, I'm going to wind up the session now. So next week, let's meet on next week, next Monday, 1:30, 3:30, right? Okay, thank you for participating.
Thank you, madam.
Thank you, madam.
Thank you,
Thank you,
madam.
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 Thank you, madam.
Okay, you're welcome.